Is it possible to focus an electron beam using mostly off-the-shelf plumbing fixtures? As you can see, it is indeed possible. It is just a lot harder than I originally anticipated. Ever since I successfully made a simple CNT electron emitter, I contemplated building a real electron gun out of it, the one which could focus a beam of electrons into a small spot. This would be incredibly useful for making another attempt at producing and observing electron diffraction, the task I am still struggling to complete. I have even read a few chapters out of this famous monograph on electron optics, giving me a strong confidence boost that focusing a beam of electrons shouldn't really be that difficult. Turns out, focusing a beam of electrons is indeed not that difficult. What is difficult is focusing it into a nice, small, round spot. As usual, I had to find it out the hard way. Probably the simplest possible electron gun is what is called Steigerwald gun. It was first described by Karl-Heinz Steigerwald back in 1949. It consists essentially of two cylindrical apertures, forming a single electrostatic lens of a somewhat larger diameter, thus keeping its aberrations low and therefore allowing it to produce a very small focused electron spot at larger distances. A near-point source heated filament thermionic electron emitter is positioned right behind the focal point of this lens, producing an image of itself some distance away. I wasn't planning to use a heated filament electron emitter. Instead, I wanted to use my CNT emitter. Turns out no one has ever made a Steigerwald gun with a CNT emitter yet, so I would be the first to try it. There are two immediate problems with using CNT emitters in this configuration. One is that they are not exactly point source, and two, they require a rather high voltage to extract the electrons out of the CNTs. Therefore, I couldn't just put a CNT surface at the same place where they originally had a heated filament emitter and expect it to work. It wouldn't. I must have felt lucky that day because I just completely disregarded the fact that I have never in my life designed a single working electron lens system, and instead I just hacked a solution by adding essentially another converging lens to the Steigerwald design, also serving as an extraction aperture for the CNT surface. The extraction aperture provides a high electric field to the CNT surface to extract the electrons. Those electrons then form a diverging beam as they pass through the aperture, because this is how single apertures work in electron optics. Hey, I have read the book. The same aperture is also forming a converging lens with the main cylinder of the Steigerwald design, thus changing the electron trajectories from a diverging to a slightly converging beam, which then gets further focused by the main Steigerwald lens. Believe it or not, but this solution has worked fine in simulation. It was time to build it. I wanted to keep it as simple as possible, which is why I started looking at those plumbing parts. They are available in both stainless steel and PTFE, therefore they are compatible with high vacuum. They are also reasonably round and are even already threaded, thus solving the alignment problem, well, at least in theory. Cutting stainless steel on a mini lathe is not fun, but it is definitely possible. Turning features which are just 1.5 millimeters in diameter is not easy either. Oops. Spot welding works great on stainless steel. This emitter pin holder is the only part which had to be machined from scratch. Even the apertures have been designed as a PCB stencil and ordered at the PCB shop. Here's all the parts before final assembly. The fully assembled unit looks kind of futuristic. Can we run it already? Well, not that fast. Going back to my hacked design, it now requires 3 separate high-voltage power supplies compared to only 1 in the original Steigerwald gun. Fortunately, used high-voltage power supplies are not that expensive on eBay, so I could afford to get 3 of them. Then a custom controller had to be made to be able to adjust all the 3 PSUs at the same time. Now we are ready for the big event. I even pre-baked all the parts before pulling a vacuum. By the way, this made absolutely no difference. Oh wait, there is one last thing. We also need a fluorescent screen. For this purpose, I used a roughly cut piece of FTO glass bonded to the regular thick sight glass with a UV-cured optical adhesive. It also helps to apply the CNT slurry to the emitter tips. By the way, why are there 2 emitters? It is because the second one is a spare. With everything finally in place, it was time to pull a vacuum, set the rough voltage levels, and then press that big red button on the PSU controller to turn the high voltage on. Can you guess what happened next? Well, exactly nothing's happened, which is why there is no video of it. There was no electron beam visible on the screen, and there wasn't even any current going from the CNT emitter. Nothing. I then pushed the voltage on the CNT emitter a little higher, and around just 8 kV, there was a faint sight of what looked like an arc somewhere inside the gun assembly, and then everything died. Like literally, the PSU controller went dark, and even my vacuum gauge controller went dark. This wasn't my best day. It then took a while to find and fix all the major issues preventing the device from running. There was bad arcing inside the PTFE housing of the emitter. The shape of that housing had to be modified, as well as the internal spacer changed from PTFE to PEEK. A separate video was made about the surface dielectric strength of insulators. This is a boring subject, I get it, but this was also the main reason the first test of the electron gun failed that miserably. With those changes, I was finally able to get the CNT emitter produce some electrons. It made a fancy electron flashlight. This was promising. Then there was this issue of vacuum dark currents. Made another video about it. A few additional fixes had to be implemented to reduce arcing from thin, high-voltage connectors. By the way, this remains a fascinating subject, and I'm still not sure if this issue can even be fixed in principle. Finally, the electronics of both the PSU controller and the vacuum gauge controller had to be properly hardened against EMI. This is how one gets familiar with those TVS diodes. It takes 1 TVS diode and 1 resistor to protect one connection going outside of the enclosure. I had about 3 dozen of those. That took a lot of TVS diodes. On top of that, both plastic enclosures also had to be coated with conductive paint. With all these changes, the PSU controller may still occasionally hang following a heavy arcing event, but at least it no longer gets fried. It was now time for the second test. This time I have at least got the electron emission going, as evidenced by the fluorescence of the vacuum grease. I just didn't have fluorescence anywhere on the FTO glass where I'd expect the actual fluorescence to happen. Why would that be? I guess the reason is that the FTO glass is not just fluorescent, but also very conductive, and therefore its entire surface immediately becomes negatively charged the moment it is hit by an electron beam, even at one tiny place. This is very different from the behavior of a typical phosphor screen, which can tolerate being hit by electrons without starting to repel them immediately. Anyway, the fix was straightforward. Connect that conductive FTO surface to the ground with a piece of wire. As you can see, this definitely made a difference. Finally, with the electron emission going and the fluorescent screen now working, I just had to play a bit more with the voltages to eventually get this. This was clearly a focusing action. Yes, the beam shape was obviously far from round, but still, this was a major milestone. Observing it a bit more, the beam wasn't just not round, its position was also very unstable. What could be causing an unstable beam position in a system where all the potentials are highly regulated and stable? It could be dielectric surface charge. Looking inside the PTFE emitter body confirmed the suspicion. As PTFE gets hit by the stray electrons, it both disintegrates and it charges up, starting to deflect the main electron beam in a bizarre fashion. Having PTFE surface exposed to the electron beam was obviously a bad idea. Lesson learned. The next fix was to cut off the exposed section of PTFE thread and replace it with a section of a threaded stainless tube. Those plumbing fixtures were indeed very convenient. And then there was another test, and this time the result has been nearly perfect. Except for there still remained a couple of annoying problems. First, the beam didn't last very long. It liked to disappear after a minute or two, and then it wouldn't come back unless I cycled the system through the atmospheric pressure. And second, the beam current was very low, typically around 1 microamp, and as I tried to increase the current by pushing the emitter voltage up, the emitter started to arc. Both problems pointed towards the remaining PTFE parts still causing trouble, so I decide that I have had enough with PTFE and it should not be present anywhere near the path of the electron beam. It was time to redesign the emitter body. Here's the redesigned emitter. The trouble-causing PTFE is completely gone. High-voltage insulation has also been greatly improved. Those spacers were supposed to be made from alumina washers, but I was too impatient to wait 2 weeks for delivery and just machined them out of a peak rod. They worked fine. This is more or less the final version of the electron gun at the time of this video. Okay, this is the final version. It performs exactly the same, except it also adds a half shield to the aperture to prevent those stray electrons from traveling towards the screen and producing background illumination. At this stage, I had the gun mostly working as it should, and unfortunately, it was also time to face the ugly truth. While the gun does indeed work, it focuses the electron beam as best as it can. The way I was making my poor man's CNT emitters was just not good enough for an electron gun. These emitters end up having 2 major problems, which ultimately prevent the gun from focusing the beam into a small spot. The first problem is that they are not a point source. They are in fact 1.5 millimeters in diameter, and while this may not be a problem for the ideal system being simulated, the real system is far from ideal and it comes with many small asymmetries. The result is that the different emitting zones at the front of the emitter end up getting focused into slightly different spots, producing not a single dot but a fancy pattern which cannot be made any smaller with focusing. They call it a disk of least confusion. Hey, I have read the book. This is what it looks like. The second problem is that the emitter tip ends up being coated in CNTs not just on its front surface but on all sides. Then once coated, these CNTs are impossible to remove completely. Some of it will remain no matter what, and will start emitting electrons in somewhat arbitrary directions. Then some of those random trajectory electrons will make it through the aperture and will eventually end up focused on the screen, but not in the same spot as the electrons which have been emitted from the front face of the emitter. As a result, we will end up with a pattern like this. Or maybe like this. Or maybe even like this. Never mind, this last one is likely the result of just refocusing the gun not on the virtual point source behind the emitter, but on the CNT emitting surface. This is, in essence, a slightly magnified emission map of the CNT surface. Kinda cool. I have this emitter body where the CNT tip is supposed to be positioned flush with the top surface, but in practice it can't be positioned exactly flush, while an extra 0.1 millimeters offset here already makes a huge difference. If the tip is slightly above the surface, both the sidewalls and the outer edge become exposed, and any CNT contamination on those walls will be emitting unwanted electrons. If the tip is slightly below the surface, then the beam geometry changes, as this now adds an additional converging lens. Yes, there are some sweet spots where the CNT emitter is positioned just right to minimize production of unwanted electrons, and then the gun produces the smallest possible focused spot. But these perfect positions are very hard to find, given that any change to the position requires both venting and disassembling the system. I tried this a few dozen times, and now on a good day I can produce the final focused spot of about 1.5 millimeters in diameter. We will see if this ends up being good enough for electron diffraction. I have my doubts. To be honest, I was expecting better. Wait, What about all those videos where the beam appears to get focused down to a sub-millimeter size? Were they fake? No, they weren't fake. They have just been produced with an old CNT emitter which only had a small area of its front surface emitting electrons. Therefore, this emitter was a lot closer to an ideal point source than the fresh emitters I have then made later on. Hence, the final spot was a lot smaller. It seems like I just need to find a way to deposit a small island of CNTs right in the center of the front face of the emitter tip, something on the order of, say, 0.5 millimeter in diameter. The resulting emitter should then produce a sub-millimeter spot. By the way, here's the very first humble attempt at producing electron diffraction with graphite. Yes, it failed, but I will keep trying. Why is graphite fluorescing? I have no idea. Meanwhile, enjoy this textbook demonstration of the electron beam interacting with a magnetic field. Note the perfect 90-degree angle between the electron velocity, the magnetic field, and the resulting deflection. Thanks for watching.